Hey my dear data friends, it's Nicola from Unsupported. Welcome to the second and final part of our video series about Azure Synapse Analytics. If you remember, in the first part of this series I introduced you to Azure Synapse Analytics, which was a few years ago branded as an end-to-end analytics solution provided by Microsoft. Remember, that is a platform as a service solution provided by Microsoft, whereas Microsoft Fabric as the newest end-to-end analytics solution is software as a service solution. So in this video, we will build upon the knowledge we gained in the first video, where we introduced core components of Azure Synapse Analytics and learned some basic concepts. In this one, we are going to dive deep and examine more advanced techniques and features in Azure Synapse Analytics and how you can leverage those features to build your robust and scalable data analytics solution. Stay tuned!
Another two important features for increasing the efficiency of the dedicated SQL Pearl workloads are column store indexes and statistics. You may be already familiar with column store indexes from the good old days of SQL Server. Now, in dedicated SQL Pool, your table is by default stored as a clustered column store index, which enables a high compression rate and fast performance for analytic queries. Aside from clustered column store index, you can choose between clustered index or heap, where heap may be the optimal choice in the data loading process for creating staging tables. Last but not least, statistics help the engine to generate the optimal query execution plan. It's of paramount importance for columns used in query joins, where group by and order by clauses. Please keep in mind that while creating statistics happens automatically, updating statistics requires action from your side. So it's a recommended practice that you perform an update statistics operation once the data loading process is completed. I'll wrap this table story by compounding the list of all unsupported table features in the dedicated SQL. If you're coming from traditional SQL Server background, you may find missing some of them quite intimidating. There is no possibility to check foreign key constraints in the dedicated SQL pool, so the responsibility for ensuring the data integrity is on your side, not the database itself. Other important unsupported features are computed columns, unique indexes, and triggers. One of the fundamental features of the dedicated SQL pool is the possibility to define the way your data is going to be stored. As you might already know, a dedicated SQL pool works as a distributed system, which means that you can store and process the data across multiple nodes. To put it simple, this assumes that the parts of your table, or the whole table, will spread across multiple locations. A dedicated SQL pool supports three options for data distribution. It's a crucial task to understand the way these distribution options work, as this may have a huge impact on the overall workload performance. Let's start with the default option, called Round Robin. Round Robin randomly distributes table rows evenly across all distributions. The key advantage of this method is fast data loading, while the most noticeable downside is the fact that retrieving the data from round robin tables could require more data moving between the nodes compared to other distribution options. Also, join operation on round-robin tables may be inefficient, because the data has to be reshuffled. To conclude, round-robin tables are great for data loading and bad for querying, especially for queries that include joins. The hash-distributed table operates completely differently. Based on the value in the column which is selected for distribution, a certain row will be allocated to a specific distribution. This option enables high-level performance for queries over large tables, such as giant fact tables with millions or even billions of rows. The key ingredient for this concept to work is the deterministic hash algorithm that assigns each row to one distribution. It's important to keep in mind that each row belongs to one distribution. Unlike in round-robin tables, where rows will be evenly distributed across multiple nodes, with hash tables, number of rows per distribution may vary significantly, which means that, depending on the data in the hash column, you may have tables with very different sizes between different nodes. To wrap it up, hash tables are great for reading data from large fact tables in a star schema, including joins and aggregations. You should consider using hash tables when your table size is greater than 2 GB. One of the crucial decisions you need to make is choosing the column for distribution. When choosing the distribution column, you should take into consideration the number of distinct values in the column, data skew, and estimation of the type of the most frequently run queries. Keep in mind that once you've chosen the distribution column, you can't change it unless you recreate the whole table. To get the most out of parallel processing performance, your distribution column should check a few boxes. Many unique values. All rows with the same value will be allocated to the same distribution. Since there are 60 distributions in total, if you have, let's say, 10 unique values, you will get many distributions with 0 values assigned, so there is no benefit of parallel query processing. Not a date column. As we've already learned that rows with the same values will be assigned to the same distribution, imagine the situation where all your users are querying the data from the last 7 days. In this case, only 7 distributions will perform the whole processing work, instead of spreading that work across 60 nodes. No nulls or contains just a few nulls. Similar to previous scenarios, imagine that you have a column containing null values only. This will allocate all the rows to a single node, so there is no parallel processing at all. The third option for data distribution is the replicated table. This one is the simplest to explain. A replicated table stores the full copy of the table on every single node. Since there is no data movement between the nodes, the queries run fast. I hear you, Nicola, if the queries run fast, why don't we simply always use replicated tables? That's a fair question, so let me quickly answer it. By creating replication tables, we are basically creating redundant data. Each of these replicas has its own memory footprint and requires additional storage. This means it's not the most optimal solution for large fact tables. In a real-life world, this distribution option mostly suits dimension tables from the star schema. Although there is no hard limit on the table size you should replicate, the recommended practice is to use this option for tables smaller than 2 GB, regardless of the number of rows. While replicated tables offer fast query performance, they are not the preferred option for data manipulation language operations, such as insert, update, and delete, because each of these operations requires a rebuilding of the entire replicated table. A dedicated SQL pool provides a separation of the storage and compute power. Consequently, you can independently scale compute power from storage and vice versa. Let's kick it off by explaining how scaling out works with compute. When you provision a dedicated SQL pool, you get exactly 60 distributions provided. However, the exact compute power depends on the number of data warehouse units you select. Wait, what on earth is now a data warehouse unit? Well, this is a unit that represents the combination of CPU, memory, and I/O. The greater the number of a data warehouse unit, the more powerful it will be. Based on the number of compute nodes, the number of distributions may also vary, as you may see in the table on your screen. As you may assume, the more compute nodes you have available, the higher performance you should achieve. Now, the fair question would be, how many data warehouse units do I need? And I'll immediately give you a very straightforward answer. It depends. The recommended practice is to start with a smaller configuration, for example DW200, and then, based on the insights obtained from monitoring your workloads, define if and when to increase the number of data warehouse units. Scaling out the data warehouse will have an impact in the following areas: performance improvement for table scans, aggregations, and create table as select operations. Enable more data readers and data writers. Increase the number of concurrent queries and concurrent slots. As you may assume, there is no single golden advice on when to scale out data warehouse units. However, you may want to consider it during peak business hours. Let's say that every Monday, many users run a complex report based on the data stored in a dedicated SQL pool. In order to avoid concurrency issues, it's a good idea to increase the number of resources during that period. Afterward, you can easily scale the number down again. Also, if you're performing a heavy data loading workload or some complex transformation, scaling out the capacity will help you to complete these operations faster and have your data available sooner. However, don't think that moving this data warehouse unit slider all the way to the right will automatically resolve all your performance issues. In case you notice that there is no performance improvement or no significant improvement, your problem probably lies somewhere else, and maybe you should consider checking table distribution options. Let's now focus on examining various techniques for tuning the query performance. The first solution is the usage of the materialized views. Unlike a regular view, which computes results every time your query targets it, materialized views, as their name suggests, materialize the data in a dedicated pool, same as for the regular table. Since the results are already pre-computed and stored, queries targeting materialized views usually perform better compared to ones pointing to standard views. Not just that implementing materialized views will reduce the time for executing complex queries, what's even better, you can distribute the data from the materialized view differently than the data from the original underlying tables, which provides even more opportunities for optimization. However, as with every powerful feature, this one also comes with some trade-offs. In this case, the biggest one is the trade-off between query performance and additional costs. Don't forget that materialized views persist the data in the storage layer, while there are also related costs for maintaining these views. Indexing is another very powerful technique for optimizing queries. Assuming that you are using a clustered column store index for the table, by default, data in the index will not be ordered. There is nothing inherently wrong with this approach, because with a high compression rate and metadata stored on each row group segment, using a default non-ordered cluster column store index will still work fast. However, it may happen that there are overlapping ranges of values in multiple segments, so when the engine scans the data, more segments will be included, thus more time and resources required to complete the query. On the flip side, when you include an order clause in the cluster column store index, the engine will sort the data before it's compressed into segments, which decreases the number of overlapping values in segments. Same as in the previous case with materialized views, there is also a trade-off with order versus non-order cluster column store index. The data loading process will be slower for the order index, but the query performance will be better at the same time. Last but not least, a dedicated SQL pool enables you to leverage the result set caching feature to improve the performance of the queries. Once you turn on this feature, a dedicated SQL will automatically cache all the queries run on that specific database. What's the benefit of doing this, you might ask? Well, by storing the query result, every subsequent matching query may be served from the cache memory. This means no repeating computation, no occupying concurrency slots, and the query will not be part of the provisioned concurrency limit. There are certain limitations regarding what queries can be cached. Most noticeable, queries that use user-defined functions or queries that return more than 10 GB of data. Also, if there were changes in the underlying schemas or tables that are part of the cached result set, the subsequent query will not be served from the cache. The cache is automatically managed by a dedicated SQL pool. If it happens that the cache result set was not reused within the next 48 hours, it will be removed from the cache. In addition, keep in mind that there is a maximum result set cache size of 1 TB per database. Finally, once you're done querying a dedicated SQL pool, don't forget to pause your compute layer in order to avoid unnecessary costs. I'm in the Synapse Studio, and the first thing I'm going to do is to go to the Manage Hub on the left. Here, I have a nice overview of all the resources available. As you may see, there is only a built-in resource in there, and that is a serverless SQL pool. Remember, a serverless SQL pool is provided by default as soon as you create a Synapse workspace. So, in order to proceed, I need to provision my dedicated SQL pool. I'll click on New on the top and give my dedicated SQL pool a meaningful name. Let's call this one PS Demo. Now, the next important configuration property is related to performance level. Basically, here you are defining the processing power of your massively parallel processing engine. As you may assume, performance comes with a price, so the more power, the more expensive for you. As this is a simple demo, I'll choose an entry point level of 100 data warehouse units. I'll leave all the other properties with the default settings and create my dedicated SQL pool. After a few minutes, a dedicated SQL pool is there and ready for action. Next, under the Data Hub, I'll open my Linked Services tab and expand New SQL Script option. I'll choose to create an external table from the sample data. In this case, it's from Yellow Taxi Open Dataset. Let's create another one based on the data related to safety in New York City. And here it is, we are now able to query the external table from the dedicated SQL pool. I'll click on 3 dots and expand New SQL Script. Let's run select top 100 row statement to see how the data looks. There you go. Let's rewrite our query to perform some kind of aggregation. I'll count the number of incidents and group them by year. By default, results are displayed in a grid. However, if I click on chart, this will give me a nice visualization of the data points. This one doesn't make sense, so let's configure our chart. As you see, there are different properties that can be configured, such as chart type, category column, legend, and so on. You may notice that years are sorted in a strange order, and there is no option to change the sorting order within the visual itself. Essentially, chart option only translates grid to a visual, but there is no additional configuration for sorting. So let's go back to our query window and add order by clause. Now it makes much more sense. I can also switch the legend position and adjust the legend label. Finally, let's play around and see how data looks if we switch a chart type to, let's say, bar or column. Great, you've just learned how to perform a basic data exploration and how to visualize the data directly in Synapse Studio. So far, we were talking and explaining how to query the data from the SQL pools in Azure Synapse Analytics. Now, it's time to examine how to explore and visualize the data from the Apache Spark pool. First of all, you need to import certain Python libraries to enable data visualization. The starting step is to import matplotlib libraries. After that, you'll create a data frame, which is a foundational Python data structure. Next, you will use pandas libraries to manipulate this data frame object, and finally create a chart from pandas. In most simplified scenario, these steps would look something like this. I'm again in Synapse Studio. A Spark pool is not provided by default. I'll go to Manage Hub on the left and select Apache Spark pools. Then I'll choose to create a new Spark pool. Let's give it a proper name, like Spark PS Demo. I'll leave the node size family default option, and for the node size, as this is a simple demo, I'll choose a small size, which means 4 virtual cores and 32 GB. Let's leave everything else like it is and create our Spark pool. Congratulations! After a few minutes, our Spark pool was provisioned and we are ready to put it into action. Let's go to Develop Hub, click on plus sign on the top and select Notebook. As a first step, I'll give a proper name to my notebook. Let's call it PS Synapse Demo. Under the language, a default option is PySpark. As I'll be using a combination of PySpark and Spark SQL, I'll continue with the default choice. Let's add a first code snippet to our notebook. This one will create a data frame object that we will use throughout our demo. It's a very basic data frame containing imaginary data about the state, age, and salary. Once I run this code snippet, I need to be patient and wait for a few moments for Spark Pool to spin up and execute the code. When finished, our data frame object is ready and available for various use cases. The first thing I'm going to do is to create 3 different data objects using the same data frame: CSV file, Parquet file, and Spark table. Of course, you need to provide your own storage account details within the code. And once I've executed this snippet, let's take a look at what's created within the storage account. As you may see, there are multiple partitioned Parquet files within the storage account. From there, I can use well-known SQL syntax to run the queries against my Spark pool. The key thing is to include %% at the beginning of your code. That will instruct Spark that we are using a notebook in the SQL context. Let's run a very simple query that will retrieve all the records from our data frame object. By default, results are displayed in a grid. However, I can choose chart option and visualize the data directly within my notebook. How cool is that? You can select between multiple chart types, such as area chart, column, bar, scatter, and so on, depending on the data that you want to visualize. You can also configure other elements of the visual and select desired aggregation type, like sum, average, mean, max, and so on. Obviously, this is not a fully fledged data visualization solution, but it comes in very handy to get a quick insight into the underlying numbers and quickly identify possible outliers. Other than visualizing the data using built-in charts in Synapse Studio, you can also leverage Python built-in libraries for the same purpose. First, we need to import some Python data visualization related libraries. I've also applied some additional steps to make my dataset cleaner and more compact. Now, I can leverage the matplotlib library and its functions to visualize my data straight in the notebook. To conclude, Spark Analytic Pool is, of course, much more than a data visualization tool. However, it's good to know that we have the possibility to visualize the data during the data exploration phase, either through native charts within Synapse Studio or using special Python libraries like matplotlib and Seaborn in Spark notebooks. Before I explain how to take advantage of the T-SQL predict function for scoring machine learning models, let's first examine the prerequisites for handling machine learning tasks in Azure Synapse Analytics. First and most important, your machine learning model must be trained outside Synapse Analytics. Not only that, the model must be registered in either Azure Machine Learning or Azure Data Lake Storage Gen 2. Additionally, the model must be in an Open Neural Network Exchange or ONNX format. What's the benefit of scoring machine learning models within Azure Synapse Analytics, you might ask? Well, the main advantage is the fact that you don't have to move the data for scoring outside of the secure data warehouse. Additionally, it provides an interface for using T-SQL language and its predict function instead of writing Python code. Let's take a high-level overview of the workflow for scoring a machine learning model. First, a dedicated SQL pool needs a model that's already trained. Since the dedicated SQL pool supports only ONNX format, in case your models are stored in other formats, you need to convert them prior to using a dedicated SQL pool. For the input data, you must choose between the following supported data types. For numeric values, int, big int, real, float, and var, varchar, and nvarchar for text values. Scoring data must be in the same format as training data. Please keep in mind that complex data types, like multidimensional arrays, are not supported. Finally, make sure that input data types and names are corresponding to the data types and column names of the new prediction data. Once you load the model into the dedicated SQL pool, it's stored as a hexadecimal string value. You may expand the model data with additional columns, for example ID or description, but you should use var binary max as the data type of the model column. Here is a simple example of the table to store the model data. After that, you can use the copy command to load the model into the dedicated SQL pool. And the last step is to score the machine learning model. For that task, you can use the tsql predict function. This function takes two arguments as input: model, which can be defined as a variable, literal value, or value produced by a scalar subquery. The second argument, data, specifies the data used for scoring or prediction. In the following example, I am using a with clause to define the name of the result set for the data parameter. One of the common use cases when using predict function is to generate a score for input data and then insert these predicted values into another table. For that purpose, you can use a well-known tsql syntax that combines insert into operation with select statement. To conclude, although Azure Synapse Analytics is not a primary go-to platform for machine learning tasks, it still enables managing some portions of the workload in a very convenient way. Not just that you can leverage tsql language for scoring machine learning models, but you can also quickly and easily scale out the resources in Azure Synapse Analytics for complex business requirements related to predictive analytics.
That's all, folks. If you enjoyed this video and this series of videos, make sure to click this like button down below. Also, if you want to stay up to date with all the latest changes and features that are coming in Microsoft's data platform world, namely Microsoft Fabric, Power BI, Azure Synapse Analytics, make sure to subscribe to Data Mozart YouTube channel. See you soon!